Lecture 14, Well Data. Geophysical logs are recorded during or after drilling a well. The main purpose is to determine rock properties such as lithology, porosity, and type of fluid. Well logs are the most detailed view of the subsurface besides well cores, but they measure the local well surroundings in a radius of centimeters to meters. Seismic is not as detailed as wells, but it covers a much more extensive area. There are several types of logs, and you will learn about these in your geophysics course. The most common logs are gamma ray, GR, and self-potential, SP, which are good for determining lithology and correlating units. Neutron and density are good for determining porosity and the presence of gas. Density and sonic allow us to compute acoustic impedance and derive a synthetic seismogram along the well. Finally, resistivity is good for detecting the type of fluid such as oil, fresh water, or salty water. The correlation of well logs is a problem that may have more than one solution. This is one example. We have two wells with the same type of log, 1 mile apart, and the eastern well has an oil show. We can interpret an anticline between the wells with an oil accumulation in the crest of the structure. Or a normal fault between the wells, with an oil accumulation in the footwall block. Or the oil accumulation can be in the crest of an anticline in the hanging wall of a normal fault. Or it can be the result of a lateral variation of sedimentary facies, where the reservoir pinches against a less permeable unit. There are different possibilities. This problem is less uncertain if one has access to seismic data between the wells. Wells are very useful to bring to the seismic section detailed, accurate geological information. We should remember that the seismic section is in two-way travel time, but the well log is in depth. A check shot is a type of seismic data on the well, which is designed to measure the seismic two-way travel time from the surface to a known depth. The check shot data allow us to construct a vertical seismic profile along the well, as shown by the graph in the middle. This vertical seismic profile allows us to convert the well from depth to time, as shown in the figure to the right. We can then place the well on the seismic, as shown in the figure to the left. This allows us to identify on the seismic section the different horizons interpreted in the well. The other technique we can use to tie the well to the seismic data is the synthetic seismogram, or synthetic seismic trace. This is basically a presentation of the data contained in the density and sonic logs of the well, in the form of a seismic trace. From the compressional sonic log, we can estimate P wave velocity. Then, as shown in the figure, we can multiply the velocity and density logs to calculate acoustic impedance. Then from the contrasts in acoustic impedance, we can derive the reflection coefficients. Finally, we can convolve the reflection coefficients with a wavelet to produce the seismic trace. The wavelet is derived from the seismic data, and it must have a frequency response and band width similar to that of the nearby seismic data. Here is one example from the Wisting field in the Barents Sea. The well logs in the middle are density and acoustic impedance. The synthetic seismogram to the right is constructed by convolving the acoustic impedance contrasts with the wavelet on the lower right, which is a representation of the low-resolution seismic data. The synthetic seismogram to the left uses a higher frequency wavelet on the lower left, which represents the high-resolution seismic data. Notice that this seismogram has many more wiggles. In both cases, the synthetic trace is matched to the seismic reflectors to tie the well to the section, and mark the tops on the seismic section. Please answer these questions.